Hello everyone. Today we are going to give our final project presentation on the topic Residual Attention Network for Image Classification. Goal. The goal of this project is to perform image classification on the CIFAR 10 and CIFAR 100 dataset using a CNN-based architecture that uses attention modules stacked together. I would like to give you a brief description about attention in neural networks. So, for example, if I will give you a book, a deep learning book, and I will ask you a question from a specific topic, there are two ways to answer it. Whether you read the whole book and then will answer the question, or what you can do is you can just search for the specific keywords and specific topic in the book and give me the answer. In the second case, what we are doing is that we're trying to put our attention on some specific topic. Similarly, the neural network works in the same way. What it do is it put its attention on several input on a particular input, and and the rest of the input is blurred. Now we are going to test it on different GPUs. We are going to compare the time and accuracy on different GPU like Tesla P100, Tesla V100, Tesla. Okay. Now, solution approach. Attention mechanism has been applied to feed forward network structure to achieve state-of-the-art result in image classification tasks. I would like to give you a brief description about how does an attention mechanism work. Simply, there are three layers. One is called encoder layer, the middle one is called attention layer, and the last one is called decoder layer. In our case, the encoder layer is CNN that we are using. The CNN will get the image and encode the image into a vector representation and pass it to the attention layer. What attention layer is going to do is it will create a contextual vector and it will pass it to the decoder. What is this contextual vector now? The contextual vector will tell you about how much weight should we give to the particular input. So as the number of input and the contextual vector would be equal. So for example, for specific one input, the contextual vector would be something, and for second input, the contextual vector should be something. Benefits: increasing attention modules can lead to consistent performance improvement as different types of attention are computed extensively. You can see in the figure 1 that on the left side we are using low level color features sky mask. So what is happening in the left side of the figure, that the sky is getting blurred, whereas on the right side we are using balloon instant mask. What is happening here? The balloon is getting highlighted. Okay, the depth of the network can easily extend it to 100 of layers because we are using ResNets. Problem motivation: robust image classification by identification of relevant features to distinguish scenes from background. As we have earlier discussed, we are going to do our experiment on CIFAR 10 and CIFAR 100 dataset on different GPUs, and then we'll compare the accuracy, time on different GPUs. A novel method in which attention mechanism has been applied to feed forward network structure. So the method we are applying is novel. Background work. Attention mechanism has also been widely applied to recurrent neural network and long short-term memory (LSTM) to tackle sequential decision tasks. It has been also applied to different other like image captioning things. In image classification, top-down attention mechanism has been applied using different methods like sequential process and control gates. Technical challenges that we faced: computational requirement associated with training deep CNN-based neural network with several attention modules stacked on large data set. So the computational requirement was very high. In addition to this, deep neural network nature of our project also requires more computational power. So there were instances when we were not able to get the GPU of our desire so to do our experiments. So that was a challenge that we faced during the experiment or project.
So for the approach, we use an attention module and we stack multiple attention modules together to make the classification. And an attention module basically consists of a trunk and a mask branch. The trunk branch is where we do feature selection by using a simple ConvNet that has skip connections or residual units. And we use the mask branch to create the mask, which helps us in identifying the relevant features from an image. And we do this by downsampling the image and then upsampling it again. And the output of the trunk branch and the mask branch are combined together. And this entire sequence of process, which is one attention module, is repeated multiple times. So this diagram essentially illustrates what I described in the previous slide. So this is the input image that we have. We first pass it through these residual blocks, which do feature extraction, which is basically a simple ConvNet. So there are p number of residual blocks that we have. And then we split into a trunk branch, which is the upper part, and a mask branch, which is the lower part. So the trunk branch is where again we do the same feature extraction, but this time with t number of residual blocks. And mask branch is where we create the mask by first downsampling the image, adding these skip connections, upsampling it again, convolving it 2 times, and then adding the output of the trunk branch and the mask branch together. So this entire thing is one attention module, which is repeated multiple times before we make the final classification. So for the implementation detail, we implemented this in TensorFlow using Keras. So this is how we implemented our residual blocks and the attention block, basically by using the functional API in Keras. The residual block is a simple ConvNet that has a batch normalization unit, a rally unit, and a conv2d unit, and we repeat this pattern 3 times. For the attention block, we have these 3 hyperparameters, P, T, and R, which basically is described over here, P, T, and R. And we chose the value of these hyperparameters to be the same as that was given in the original paper. And essentially, for the number of pre-processing units, we create the residual blocks. The output of this is then passed to the trunk branch and also to the mask branch. So there are p number of residual blocks over here, and the output then goes to the trunk branch and also to the mask branch. So for the trunk branch, we again do the same residual blocks, but this time with in a loop that goes from 1 to t. And for the mask branch, we first downsample the image 2 times using the maxpool2d function, and then we upsample the image using the upsampling2d function in Keras. And the final output that we have from the mask and the trunk branch is like this. It is 1 plus output of the mask branch into trunk branch. And that is what we return from this method. And then finally, this is the create model method, where we basically pass the input size and the number of classes that we need. And we use the residual block and attention block that we implemented multiple times to create the final model. So we test this approach on 2 data sets, CIFAR10 and CIFAR100, across 3 GPUs, V100, P100, and NVIDIA Tesla T4. So the accuracy of CIFAR100 on V100 was 91.17%. For CIFAR100 on T4, it was 93.34%. And for CIFAR100 on P100, it was 90.03%. So we basically got the highest accuracy with T4, but it also took the longest training time. For CIFAR10 on V100, the accuracy is slightly low. It is around 88.45%. For CIFAR10 on Tesla T4, we got the highest accuracy of 91.07%. And for CIFAR10 on P100, it's again a bit low, which is 86.73%. So in this case also, the highest accuracy that we got was on T4, and it also took the largest training time. So this table over here summarizes our entire experiment. So for both the data sets, the highest accuracy that we get is on T4, but in both the cases, it also takes the highest training time as well. For the conclusion, we essentially try to demonstrate from the paper how we can use the attention mechanism for robust image classification by identifying relevant background information from an image. We compared the performance in 2 data sets across 3 different GPUs that were available on GCP. And this attention module mechanism has a wide-ranging applications in areas where the scene or the background information is relevant. And it is also widely used in LSTM for image captioning. So that concludes our presentation. Thank you.